So I begin by welcoming you to our institute. Now this is the coordinators workshop, so here we'll try to give a flavor of things to come in the main workshop. So I'll start the first topic, which is on fluid statics. All right. Now in the morning, Professor SGM had defined a fluid as a substance which deforms continuously under the action of a shear stress, no matter how small that stress is. Even if it's infinitesimally small, the fluid will deform. That means it will start to move. So if the fluid is at rest, then the shear stress will be zero on any plane. So if you look at tau xy, that is going to be 0. If you look at tau yx, that is also going to be 0. Similarly, tau yz, tau zy, tau zx, and tau xz, these are all going to be 0. Now let us look at the normal stresses. Now we will consider a fluid element which is in the form of a wedge. So let us say this is the direction of gravity. So I will put a bar on top to denote vectors. So this is the direction of the gravity vector. Now suppose I say the y-axis is vertically upwards and the x-axis is horizontal. Now consider a fluid element which is in the form of a wedge. So in the third direction, which is perpendicular to this plane, let us say the thickness is a unit depth. Okay, so it's like a prism. Now we'll consider the equilibrium of this fluid element, which is at rest. So since this element is at rest, the sum of the forces acting on the element will be 0. Now Professor Chakravarti mentioned that there are two types of forces acting on a fluid element. One is the body force. So here it is simply the weight of the fluid which is inside this triangle. So if I call this O, if I call this A, this B, this has three surfaces, OA, AB and B. So in addition to the body force, you are going to have surface forces exerted by the surrounding fluid. So the fluid which is all around this element is going to exert a force on these surfaces. Now we are saying the shear stresses are 0, so we are going to have just the force due to the normal stresses. Now this is the negative x phase. The outward normal is, if I say this is the unit vector is I, this unit vector is j, then this is the minus I phase and this is the minus j phase. And this inclined surface, the orientation, you can describe by the outward normal we'll call n hat. Okay. So in my notation, this caret sign or the hat sign indicates a unit vector. So the magnitude is 1. Now let us say I draw a line here parallel to the x-axis and a line parallel to the y-axis. Suppose I say this angle is theta. Then since this magnitude of this vector is 1, you can say that n is cos theta I plus sin theta j. Now since this angle is theta, this angle here is going to be 90 minus theta, so therefore this angle is going to be theta. And this is an alternate angle, so this angle is going to be theta. Now let us look at the forces which are acting on this. So I'll draw a bigger figure. So this is the inclined surface described by this unit normal n, and there's going to be a force on this surface, the surface force, which is going to be perpendicular to this surface. So let us say this direction is, and here the force is going to be perpendicular to this surface, and the surface force here is going to be in this direction. If I say this is x, this is y, this is the origin O, suppose I say this is F1, the net force exerted through this surface, which we call OB, on the fluid which is inside this triangle, and let F2 be the force. So I am showing the direction as F1. If you find it is negative, that means it will point the other way about. Okay. And similarly here, you may have a force which is F3. Now, if this is a very small surface, okay, the stress may be assumed to be uniform here, and then this F1 will be the normal stress on this surface into this area. If it is a large surface, the stress might vary, and then you have to integrate over the surface. Now, if I come back to the figure which I drew earlier, suppose I say AX is the area of the surface which is perpendicular to the x direction. So by AX I mean the area of this face OB. This is the face which is perpendicular to the x direction. So the subscript denotes the normal to the face. And let us say AY is the area of the surface which is perpendicular to the y direction. And similarly, let us say AN is the inclined area AB. So that is the area of the surface perpendicular to the unit vector n. Now, if I say that L is the length of AB, let us say, then you can see that AN will be L into 1, because we are taking an element of unit depth in the third direction of the z direction. Now, if I come back to this figure, which is a larger figure, we are saying that this angle is theta. Okay. So, what will be AX? AX will be the length of OB, this length, into 1. Now, if this is L, then this is going to be L cos theta into 1. And similarly, AY, which is the area of the face perpendicular to the y direction, there are three faces here. So this face, there is the length of OA into 1. Now, OA is the length of AB into sin theta, L sin theta. And AN, which I wrote earlier, I am writing here for convenience again, is L. So you see that AX by AN is cos theta, and AY by AN is sin theta. Now, since the surface forces are proportional to the area, we are looking at the areas. Now, what is F1? F1 will be the stress here, which you can call sigma xx. I'll put a star here on top to denote that it is some average value of the normal stress on this surface OB. So it will be this into AX. Similarly, if you look at F2, it will be sigma YY. So I'm using the notation which was followed by Professor Chakravarti in the morning. So this is the phase perpendicular to the y direction. So normal stress in this direction is sigma yy multiplied by ay, that is the net force. Now this angle here is theta. Okay. So let us look at the sum of the forces in the x direction, which is acting on the fluid element. Now I started by taking the y-axis vertically upwards. So the body force is in the y direction. It has no component in the x direction. So if you look at the sum of forces in the x direction, you are going to get a contribution from this face OB and this face AB. The surface forces are on these two. The surface force on OA is in the y direction, so it will not contribute to the sum in the x direction. So this is going to be F3 cos theta minus F1, because we know there is no shear stress on any surface, so we know the direction of the forces. The direction of the force is going to be normal to the surface. So if I look at the inclined surface, I know the force is going to be normal to this. Okay, and this angle is theta. So this must be equal to 0, because the fluid is in equilibrium. This element of fluid is in equilibrium. So we are going to get F3, we have written as, you can write sigma nn, where sigma nn is the normal stress on the inclined surface, some average value into an. So what you have from here is that sigma nn star an cos theta minus sigma xx star into ax is equal to 0. So that gives you a relation between sigma nn star and sigma xx. Now an is L into 1 and ax is L times cos theta. So if you multiply an by cos theta here, this will cancel with ax. So from here you have sigma nn star equal to sigma xx star into ax by an cos theta. Now ax by an is cos theta, so this cancels out. So we get sigma nn star equal to sigma xx star. Now similarly you can do a sum of forces in the y direction. So let me draw that figure again. This is the horizontal direction, this is the vertical direction. This angle is theta. This force I call F1. So this will not this surface force will not contribute to the sum of forces in the y direction. Now I want sum of forces in the y direction. So this force on this surface I call F2, and the force here in this direction I call F3. Now if this angle is theta, then F3 will have a component in the vertical direction which is F3 sin theta. So you are going to have F3 sin theta minus F2. So these are the contribution to the net surface net force in the y direction from this surface and this surface. The surface force on this side, which is called OB, is in the x direction, so it doesn't contribute to this. But now you have to consider the weight also. We are saying the gravity is in this direction, so minus, let us say, mass of the liquid here, or maybe a gas, whatever it is, mass of the fluid in this surface element is m, then you have to, that is going to be downwards, so minus mg. This is the net force, which must be equal to 0. Now again, F3 we wrote as sigma nn star, some average value, into an, and there is a sin theta coming here from this, minus this F2 is sigma yy star the average stress on this surface OA into AY minus this I can write as the average density times the volume of this element into G equal to 0. Now once again from here we have sigma NN star. Now if I go back and flash again this relation, we have shown that AY by AN is sin theta. So AN sin theta is nothing but AY. So I can write it as AN AY minus sigma YY star AY minus rho star into V into G equal to 0. So from here we get another relation for sigma NN star. If I bring these two terms to the other side, we are going to get sigma YY star plus rho into rho star into V into G divided by AY. Now AY I can write as AN sin theta. So I can write it as sigma YY star plus rho star, let me write the G first, into V by AN sin theta. Now what we will do is, we will take the limit of a sequence of wedges or prisms, whatever you call it, of progressively smaller size. And to keep them geometrically same, we will keep the angle the same so that this sin theta remains the same. So what I mean is that, you consider for example, this is one element, we will take another element like this with a size which is parallel to this. Then we will take another one and another and so on. So we will consider the equilibrium of not one prism but a sequence of prisms of smaller and smaller size, but they are all geometrically similar. So these are all similar triangles. All of them have a face which is perpendicular to the x direction, one face perpendicular to the y direction, and one inclined surface whose orientation is the same, so that this theta is the same. Now what will happen is, when you shrink the size to a point, these average values, which I call denoted by stars, which are the average of stresses over the surface, they will become the value of the stress at the point O. Okay. So this will become the local value, this will become the local value. And if I go back to my previous relation, this star will also become the local value. This will also become the local value. Now, this rho star also will become the local value, but you tell me what will happen to this ratio V by A as the size goes to 0. So V will go to 0, A will also go to 0. So you have over here 0 by 0. Now if you have the ratio of two quantities both going to 0, then the ratio could be 0, infinite, or some finite non-zero number, depending on the rate at which they go to 0. Now the volume will go to 0 faster than the area. So this term in the limit will go to 0. So we will get sigma NN equal to sigma YY. Now if you have difficulty in following this, let us go back to this slide, and we have written AN as the length of this inclined surface, here this line AB into 1. Now you tell me what is the volume. V of the fluid here. This is going to be the area of this triangle OAB into 1. Okay. Now what is the area of the triangle OAB? It is going to be half into OA into OB into 1. Okay. Now OA is L cos theta. So this is half L cos theta, and OB is going to be L sin theta. So this is L sin theta into 1. So the volume is half L square sin theta cos theta. So let me come back here and write V as half L squared into sin theta into cos theta, and AN is simply L. So if you look at the, as L goes to 0, AN goes to 0, V also goes to 0, but this is going to 0 as L squared, and this is going to 0 as L. So if you look at the ratio of V by AN, it is going to have half L squared by L, which is L, into sin theta into cos theta. Now we are considering a limit where the angle is fixed, so this term remains fixed, and as you shrink the size towards 0, the length of this line is going to go to 0. So the ratio you can see is proportional to L, so that goes to 0. So in the limit, the effect of the body force is not there. So this will give you sigma NN star equal to, or rather sigma NN equal to sigma YY. Because once you take the limit, the average value will become the local value, and you have shrunk it to the point O. So the net result is that you are going to have sigma NN equal to sigma XX equal to sigma YY. Okay. Now we have taken X to be the horizontal direction and Y to be the vertical direction. So the XZ plane is the horizontal plane. So you can do a similar analysis in the Z direction. Okay. If you want, you can rotate the coordinate system. Whatever you are calling X, you can call Z. Okay. So ultimately you are going to have this also equal to sigma ZZ. Now if you don't like my argument here, you can do a 3D analysis by taking a tetrahedron. So if this is X, this is Y, and this is Z, this is origin, you can take a fluid element whose shape is in the form of a tetrahedron. So this will now have 4 surfaces. One inclined surface, so if I call this A, if I call this B and C, ABC is the inclined surface, and the other 3 triangles, they are perpendicular to the X, Y and Z direction. Excuse me. And you can repeat the analysis similar to what I did. To save time, I started with the 2D, and then of course it's easier for you to see. You will get the same relation. So here you will take a sequence of tetrahedra such that their inclined surface always points in the same direction, L. So sigma NN is the normal stress on the inclined surface. So once you shrink it to a point, at a given point, through a point you can have infinite number of planes. Okay. So what we are showing here is that the force per unit area on any plane is the same at a point. It's independent of the orientation of the plane. So this is what you are familiar with as your Pascal's law. Now, Professor Schumann mentioned in his introductory lecture that while a solid can sustain tension, a fluid at rest, it cannot sustain tension. So this normal stresses are going to be compressive. Okay. So if I draw a fluid element in the form of a rectangle, if I say this is X and this is Y, you know that if the sigma axis is positive, then the force here, surface force on this plane, is going to be in this direction. And as Professor Chakraborty mentioned, the negative X plane, that is the plane whose outward normal is in the negative X direction. If the force is in the negative X direction, then the stress is, if the stress is positive, the force will be this way. Now, this, if the sigma axis is positive, so I have shown the direction of the normal stresses on these two faces when sigma xx is positive. So I can see that the stresses are trying to pull these surfaces apart. So this is a tensile stress. Now if you have a similar thing, let us say I draw a rectangular surface here, and the sigma axis is negative, then it will act this way on this surface. If it is negative here, it will act on this surface. So this is the case when sigma axis is negative. Now you see that these two forces are tending to push these two surfaces together. So this is a compressive thing. So this is what will happen here. So all these terms, these four terms, then are going to be negative. And the magnitude of that is what you call pressure. So we'll write this as this equal to minus P, where P is a positive quantity. So these are all the stresses at the point O, and this P is also the pressure at the point O. So now if I make a summary of what is called the hydrostatic stress distribution, you are going to have sigma xx equal to sigma yy equal to sigma zz equal to minus P. And you are going to have what I wrote earlier, tau xy equal to tau yx. Now of course later we will show that for a Newtonian fluid, even if the fluid is deforming, this is still true, that is the stress tensor is symmetric. This will be equal to 0, and similarly tau yz, which is going to be equal to tau zy, this also is going to be 0. Likewise tau xz and tau zx, they are all going to be 0. Now if I write the stress tensor, I can use the index notation, or I can write it in the form of matrix, 3 by 3 matrix. All right. Now in the morning, Professor Chakraborty used the index notation. So this one, sigma xx, what I call sigma xx, and as he mentioned, some authors may write similarly sigma x. Okay, but I prefer to write two subscripts. So sigma xx is the same as tau 11. So this will be equal to tau 22, which is the same as sigma yy, and this is the same, tau 33 is the same as sigma zz. This is going to be equal to minus P. And instead of writing tau xy, I can write tau 12. So this will be tau 21, which is the same as tau yx, and this will be equal to tau 23, which is the same as tau yz, equal to tau 32, which is in a new notation for tau zy. This will be equal to tau 13 equal to tau 31. This will be equal to 0. So what you see is that tau ij equal to 0 if I is not equal to j. When I equal to j in this notation, it denotes a normal stress. So normal stresses are not 0, they are equal at a point. And if I not equal to j, they denote this tau ij denotes a shear stress. So you can see here 1, 2, so there 1 is not equal to 2. Similarly, this is 2, 3, and this is 3, 1. So if I not equal to j, it is 0, and if I equal to j, it is minus P. Now there is a standard term called Kronecker delta. You denote it by delta ij, which is 1 if I equal to j, and 0 if I not equal to j. So you see that this I can write in one line as tau ij is equal to minus P into delta ij. So when I not equal to j, this is 0, and when I equal to j, delta 11 is going to be 1, and this is tau 11 will be minus P. If I put I equal to j equal to 2, delta 22 is going to be 1. So this is tau 22 equal to minus p. And similarly, tau 33 is minus p. So this 9 equations which I wrote over here, 9 relations rather, 6 for the shear stress and 3 for the normal stress, I can write in a compact fashion as tau ij is minus p delta ij. So this is the stress distribution in a fluid which is at rest. So at each point, tau ij is minus p at that point into delta ij. Now I can define a stress tensor which I will denote this way, T with the 2 bars on top. So this is a 3 by 3 matrix. So we can write it as, in this notation, as tau 11, tau 12, tau 13, tau 21, tau 22, tau 23, tau 31, tau 32, tau 33. So there are 9 components, 3 squared. So because it's a tensor of rank r has 3 to the power r entities. So if you look at a scalar, r is 0, so 3 to the power 0 is 1. So it is a tensor of rank 1. Now if you have a vector, it has 3 components, so r equal to 1. Of course, any entity with 3 components is not a vector. It will transform according to a certain law when you make a coordinate transformation. Similarly, here this is a tensor of rank 2, so it has 3 square or 3 to the power 2 elements, and it transforms according to a certain law. Now, so this I have arranged in the form of a matrix over here. Now, this if you write, this tau 11 is minus p, so all the diagonal elements are minus p because they represent the normal stress which is negative. So p is positive here, and the odd diagonal elements which represent shear, these are all 0. So if you want, you can factor out the minus p here and write it as p into 1, 1, 1 on the diagonal and zeros. So this is what we call the identity matrix. So I can write it as minus p into I with 2 bars on top. So this is what is referred to as the hydrostatic stress distribution. Of course, the term hydro refers to water, but it is used for any fluid. All right. Now we need to find what is the pressure distribution in a fluid. We have just found the form of the stress tensor at a point. The value of P will vary from point to point, so the stresses will also vary from point to point. So let us first find what is the net surface force due to pressure on a fluid element. So we look at the net surface force on a fluid element. So let us start with simple cases, then we'll go to more general cases. Suppose I have a fluid element which is in the form of a rectangle. And let us assume that the pressure variation in the fluid is such that the pressure is a constant. Okay. Then if I show the pressure distribution on this face, it's a distributed force. So these are the arrows which show the direction of the force. It's a compressive force, so it will, if the fluid is inside this element, it will act normal to the surface and inwards. Okay. And on this surface also it will act inwards because it's a compressive force. Similarly, if I look at this surface, it will act inwards. So this is a distributed force, and here also it will act this way. Now if I ask you what is the net surface force on this fluid element, what will you say? The force on this surface is pressure into the area. The force on this surface is also the same pressure into the same area, and they are acting in opposite directions. So it will cancel out. So the first thing you have to understand is that there is going to be a net force only if the pressure is varying from point to point. If the pressure is not varying from point to point, then the net force is going to be 0. Now when the fluid is at rest, the weight of the fluid is balanced by the pressure. Okay. So therefore there must be a net force in the vertical direction which balances the weight of the element. So therefore in a fluid which is at rest, in the vertical direction the pressure is going to vary. In the horizontal direction there is no body force, so you will see that the pressure variation in the horizontal direction is not there. The pressure will vary only in the vertical direction. So to get an equation which you can solve to find the pressure distribution, now you have to find the net force on a fluid element in terms of a pressure field. So we'll introduce what is called a pressure field, which is a function we'll call P of x, y, z. So this function will tell you what is the pressure at any point. So if you want it at the point say 1, 1, 1, x, y, you put here coordinates 1, 1, 1, you get the into the function you get the value of pressure at that point. If you want the pressure at the origin, then put x0, y0, z0. Now the fluid is at rest, so this does not depend on time. It depends only on the spatial coordinates. Now let us say I have a general function which I call P of x, y, z. Can we develop an expression for the net force in terms of P or maybe some derivatives of P? So that is what we have to do. Now once again I'll start with a simple case. Suppose I take P to be a function of z, one coordinate. Okay. If I say z is this way and x is this way, now I take a fluid element here. There is a force below on this surface, and there is, which is going to be upwards because it's a compressive force, and there is going to be a force here. Now I am drawing a larger arrow. It is inwards because it's compressive. To give you the impression that there is a net force, I have deliberately drawn this line, and the length of this arrow larger. So if you have a distributed force here, you have the magnitude here smaller than the magnitude here. Okay. Now if I say this face, the value of z is say z equal to zl for lower, and the value of z here is z equal to z upward, let us say. And let us say this distance, this length is delta z. So this bottom pressure I will call PL, the pressure on the lower surface, and this I will call PU, the pressure on the upper surface. So what is the net pressure force? So I will say F pressure comma net as the net pressure, net force on this element due to pressure in the z direction. Okay. Now of course if P is varying with z only, there is no net force in the other direction. That is obvious. So this is going to be equal to PL into this area of this face minus PU into the same area. So this is PL minus PU into the area. I can factor out this area. Now we are saying P is a function of Z. So what is PL in terms of this? PL will be P of ZL. I give you a function here. I have to find this by solving a differential equation later on. So for the timing, I am denoting it by a function. And since the fluid is a continuum, this function is going to be a continuous function of Z. Similarly, Pu is the pressure when Z equal to Zu. So ZL and Zu are the coordinates of the bottom face and the top face of this. Now Zu is ZL plus delta Z, because I am using delta Z, the symbol, to denote the length of this element in the vertical direction. Now if this is a continuous function, I can expand it in a Taylor series about ZL. So this I can write as P of ZL excuse me, plus dP dZ evaluated at ZL into delta Z, plus, if you want to write another term, half d2p dz squared at ZL into delta Z squared plus dot dot dot. Okay. Now you note that this first term on the right hand side is nothing but PL, what I wrote over here. So here the net force is the difference in the pressure into the area. The area is the same of this, area of these two faces is the same. So net force is there if there is a difference of pressure. If the pressure is not varying, then the net force is 0. So what is PL minus PU? This multiplied by the area will give you the net force. So to get it, I move this term to the left hand side, and then I will be left with the infinite series. The first term of this is dP dZ at ZL into delta Z. And then you have higher order terms, half d2p dz squared ZL into delta Z squared plus this. Now what is this area? We are taking a small rectangular element. So this area is delta x into delta y if you take a 3D element, because this is a surface which is perpendicular to Z, so there is no Z over here. So if you want the PL minus PU into the area, okay, I will go to the next page maybe. So PL minus PU into the area will be dP dZ evaluated at ZL into delta Z into delta X delta Y, which is the area, plus half d2p dz squared delta Z squared. Of course, this is evaluated at ZL into delta Z squared into delta X delta Y plus higher order. So the left hand side here is the net force due to pressure in the Z direction. So you see that that is this pressure gradient dP dZ into the volume. This delta X into delta Y into delta Z is the volume of the fluid element. So if I want F pressure net in the Z direction per unit volume, let us say, then it will be dP dZ at ZL plus half d2p dz squared at ZL into delta Z plus higher order terms. The delta X, delta Y and one of the delta Z's will cancel out. Now we had argued before we got this mathematical expression that if the pressure field is uniform, that is the pressure at all parts is the same, net force should be 0, because one acts in upwards, the other acts downwards. And that's what you see. If P is a constant, then dP dz will be 0, d2P dz square will be 0, and other higher order terms will have higher order derivatives, all of them will be 0. So net pressure force will be 0. Now, to develop what is called the basic equation of fluid statics, we'll look at this net pressure force per unit volume in the limit as delta V goes to 0. So we want limit as delta V goes to 0. That means delta X, delta Y, delta Z all are going to 0 of this F pressure net. And I have started with a simple 1D case where there is only force in the Z direction divided by delta V. Now, when you take the limit, what will happen is this will go to 0 because it has multiplied by delta Z. The other term, next term will be proportional to delta Z square, that will also go to 0. So you will get simply dP dz at Zn. The other terms have gone to 0. So dP dz represents the net pressure force per unit volume on an infinitesimally small fluid element in the Z direction. Now we have to generalize this result to cases where P is varying with X, Y as well as Z. Okay, now nobody said anything when I did it, but you come back over here and see that this was Pu and this was Pl. Okay, so the expression which I wrote here is not Pl minus Pu, but it is Pu minus Pl. So this is Pu and this is Pl. Okay. So you come back over here and all you have to do is put a minus sign here. Okay. So you have a minus sign here. So what is the physical meaning of this minus sign? If dP dz is positive, that is the case which I drew over here. This is the Z is pointing upwards. So if pressure dP dz positive, that means as Z increases, pressure increases. So the top face, the top pressure here is more than the bottom pressure here. In that case, the net force will be downwards, that is in the minus Z direction. Okay. If the pressure is decreasing upwards, then this Pu will be less. Then you will have a net force upwards. All right, now let us look at a general case. So first I'll give you a heuristic proof. So let us say I look at a fluid element whose surfaces are perpendicular to the coordinate axis. So if I say this is X, this is Y, and this is Z, let us say. This is the element of fluid. Now, we want the net pressure force on this. We'll find it in one particular direction and then you can write an expression in analogous fashion for the others. So let us say I want the force in the X direction. Okay. Now this fluid element has 6 faces. A pair perpendicular to the X direction, a pair perpendicular to the Y direction, and a pair perpendicular to the Z direction. Okay. Now if you consider the faces which are perpendicular to the Y direction, the net force will be in the Y direction because these are only normal stresses if the fluid is at rest. Okay. Now even if the fluid is moving and we want the net force due to the pressure, alright, the pressure force is acting normal anyway. Okay. If the fluid is moving, there will be other forces which you have to consider. So the pair which is perpendicular to the y direction will not contribute to the x direction force. Similarly, the pair which is perpendicular to the z direction will not contribute to the z direction force. So the net force, if you want, say F pressure net. Okay. Now let us say this I want in the x direction. This will come only from the forces which are acting on this face perpendicular to the x direction and this face perpendicular to the. Now if I say this right point, the center of this right face is say R and the center of the left face, or let me say I call this say east face E and I call this west face. Now this pressure force, if I ask you, a simple minded way is you take the pressure at the midpoint times this area. P at the east face into the area which is perpendicular to the x direction. So this will act in this way, inwards. So there is a minus sign. Okay. And the force here will act this way. So plus P on the west face into Ax. So what we want is the difference, if you factor out the minus sign, minus Pe minus P west into Ax. Now if the pressure is varying in the x direction, only then there will be a difference in the east and west pressures. Okay. Now here Pe I can write as P of Xe, Ye and Ze. Now I am taking P to be a function of x, y, z, and P west will be P of x west. Now these, if you look at this point and this point, the y and the z coordinates are the same. They differ only in the x coordinates. So I am going to write only Ye and Ze. And Xe I can write as x west plus delta x. So I can write this as P of x west plus delta x, Ye and Ze. So if you want the difference in the pressure between the midpoints, say Pe minus P west, okay, what you are going to have is P of x west plus delta x. So x west is the coordinate of the point I am calling W here, and some y coordinates minus P of x west, Ye and Ze. Okay. So in these two functions it has three arguments x, y, z. So the y and the z are fixed, they are the same for the east and west point, they are differing only in the x coordinate. So if we expand this, again if we say it is a continuous function, this will be P of xw, ye, ze plus del p del x at xw, ye, ze delta x, and I will not write the other term because you have seen it goes to 0, so plus dot dot dot. So this infinite series represents the expansion for the first term, and from that you are going to subtract P of x west, ye and ze. So you are going to get this term cancelling with this term. Now I use the symbol Ax to denote the area which is perpendicular to the x direction. So what is Ax? Ax is the area of the, this length is delta z and the vertical length is delta y according to this figure. So this is delta y into delta z. So you are going to have Pe minus P west into X is equal to del P del X. What you have over here, I am not writing, okay, let me write it, X west, Y east, Z is whatever it is. There is a delta X already sitting here. You are now going to multiply it by delta Y, delta Z, and you have other terms. Okay. Now, if you want the net pressure force here, you have to put a minus sign here. So, minus of this will be minus of this plus higher terms. So, now what we want is F pressure, the net, that is the net force due to pressure in the X direction by delta V, which is the volume of this. So, if I go back over here, this product is your delta V. So, if you divide by delta V, you will have simply minus del P del X. Minus del P del X evaluated at some point and some higher terms. These terms will go to 0 if you take the limit delta V going to 0. So, you are going to have limit delta V going to 0 of F pressure net X by delta V is equal to minus del P del X. Now, once you shrink delta V to a point, this will be del P del X at that particular point. So, I am simply writing del P del X. Now, similarly, if I want the Y direction force, the net force, you are going to get del P del Y, and the Z direction is del P del Z. Now, earlier I was writing dP dz because I started with a simple case where P varies only with Z. Now, we have got the general thing. Now, if I say F vector is the resultant force which has the x, y, z components all, net by delta V in the limit as delta V goes to 0, then you are going to have from the x direction force minus del P del X I, from the y direction minus del P del Y J, and from the z direction minus del P del Z K. So, this I can write as minus grad of the function P, or I can write it as minus del of P, where grad P or del P is this function del P del X I plus del P del Y J plus del P del Z K. So, this is what we want. Now, let us see how this will help us in finding what is grad P. So, we have just denoted the pressure distribution by a function which we call P of x, y, z. We do not know yet what is the function. That you have to get by solving a differential equation. So, we will look now at what is called the basic equation of fluid statics. Yeah. The one before this.
X of delta x is there. Are you getting my point, sir?
Huh? Which one? This?
Yes, sir. So P of xw plus delta x is there.
Yeah.
and y x is there. So you have cancelled out p in terms of x, y, z, but you have written again dou p of dou x, x w, y w, x z. But in fact, only p of delta x is there. How that y terms and z terms comes?
So this is the Taylor series expansion. See, delta y is 0 and delta z is 0.
Okay, okay.
Because the y coordinate and the z coordinate is the same. Okay. Now, of course, here I had made an approximation that I said this is a heuristic proof because I wrote the pressure as the net force as the center point pressures. Now, I was going to skip it because due to lack of time, but since you mentioned, let us look at a general case. Suppose I have a fluid element of this form. Okay. What is the net force on this? Now, if I take a small area element here, dA. Okay. Now, this is a curved surface, so each area element will have a outward normal which is pointing in a different direction. So, this is say the normal vector perpendicular to this element. Okay. Now, if you look at the force here, the pressure force is going to be downwards. Okay. So, dF due to the will be dFs, let us say, for the surface force is going to be minus P n into dA. The magnitude of the force is the pressure at this point, P into dA, and it is a compressive force which is acting normal to the surface, n is outwards, so you have the minus sign. Okay. Now, what you want is the net force. Now, I am not writing the subscript x, y, z, it is the net, I am dealing with vectors. This you will get by integrating this over the entire surface. So, this is the area integral. So, you have to take different area elements, they will have different orientations, so the direction of the forces will also be different, magnitude will also be different. So, P multiplied by n, this n takes care of the direction, dA if you integrate you get straight away the total force. Now, this we can convert to a volume integral as minus grad P dV using the divergence theorem. Okay. Now, if you use the mean value theorem, I can write this as minus grad P at some point inside this volume into the volume. Okay. So, F pressure net by the volume is minus grad P, the value of this evaluated at some point inside. Now, if I take the limit V goes to 0, then this star value will become the local value. This will be minus grad of P. So, this is a rigorous thing. The other one I gave you is a heuristic thing which is giving you a physical picture, but it is a faulty derivation. This is 100% correct. But this is assuming that you are familiar with this divergence theorem in this form. So, the previous derivation which I did, although not very rigorous, it is giving you the right result. Okay. And physically also, you see that if P is constant, it is a uniform pressure field, then we had argued earlier the net pressure force is 0, and that is what you have. Okay. Now, let us go back and look at this basic equation of fluid statics. Now, here we will consider the equilibrium of a fluid element. So, here you have the net force due to pressure plus the body force equal to 0, because there is no acceleration. The fluid element is at rest, it's in equilibrium. So the sum of the forces is 0. You have the force due to the body weight of the fluid element and the pressure force.
P minus PW.
Okay, let me go back to this.
Yeah. In that the second term would be plus, and then again it will appear negative.
This
Okay.
one?
Okay, second term is plus. Okay,
This?
sir. Okay. But it is multiplied by a negative sign both the sides, I think, in the next term.
No, here is minus because I have a minus sign here. This is minus P plus P.
Okay, thank you, sir.
I put a minus sign here because the net force is minus. Okay. Now, this net force due to pressure, I can write as minus grad P now into the volume. If I take a, or you can take it to be dV if you want, take a infinitesimal volume. And this you can say is mg. So the mass is rho dV into the gravity vector equal to 0. Okay. So it is minus grad P plus rho g into dV equal to 0 for an infinitesimal fluid element. So this is the net pressure, minus grad P into dV is the net pressure force, the net surface force, and this is the net body force. The mass is rho v into g. Now this must holds for all dV, so you have minus grad P plus rho g equal to 0. Or you can say grad P is equal to rho g. So this is the basic equation of fluid statics. Now if you solve this equation with appropriate boundary conditions, you will get this function P, the pressure field in the hydrostatic state or the fluid static. Now let us find this for a simple case. So let us say most of the books will take the z direction to be vertical and upwards. So let us say the xy plane is horizontal and you have gravity acting downwards. So I am putting a bar on top to denote the vector quantities. So here if I say this is I, the unit vector, this is j and this is k, then according to this coordinate system my g is minus gk. So this equation then will be, according to this coordinate system, del P equal to minus rho g k. Now this is del P del x I plus del P del y j plus del P del z k. How about to put it on? Minus rho g k. So we have a vector equation now, and the right hand side has only the k component, so that means del P del z will be minus rho g if you equate the k components. Now since the right hand side has no I and j component, del P del x and del P del y will be 0. So for this particular coordinate system, you are going to have del P del x equal to 0, del P del y equal to 0, and del P del z is equal to minus rho g. Now the first two equations are telling you that the P is not varying with x and the P is not varying with y. The physical reason for that is the xy plane is the horizontal plane and there is no body force in the x and y direction. So this equation is a balance between the net pressure force and the body force. There is a body force in the y direction, z direction, which is the vertical direction. So it is very. So this these are partial differential equations. But because P doesn't vary with x and y, these two imply that P is a function of z only. We started with a general function P of x, y, z, but the equations are telling you that it doesn't vary with y and z. So that means instead of writing del P del z, I can write here dp dz is equal to minus rho g. So now we have brought it down to an ordinary differential equation, which is much easier to solve than partial differential equations. Now let us say, let us take an example. Suppose we have, say, water in a tank. This is the ground level. This is a z, this is x, and you have y maybe in this direction. And this height might be, say, h, total height. Now let us say above here we have air. Now this equation is telling you that dp dz is minus rho into g. Here are two fluids, water and air, and you know that rho of water will be about order of 1000 kg per meter cube. Okay, maybe 990 or whatever it is. If you have some salt dissolved, it will be different. But order is 1000 in SI units. Now rho of the air will depend on the conditions, temperature and pressure. So normally it will be about 1.2 or order of 1. So the variation of pressure, this is the hydrostatic variation of pressure with Z is going to be much less in the air than in the water. So we will neglect it in the air, and we will say that at the free surface or the surface interface between the air and water, we will say the pressure is a constant which you can call atmospheric pressure. Of course, you know atmospheric pressure also will vary with height, but the length scales over which varies is very large. Okay. So we will say that we will solve this equation with the boundary condition. Say at z equal to h, if I put z equal to 0 at the bottom of the tank, z equal to h is P is, say, P atmosphere. Now if I integrate this, we will get P of z is equal to minus rho gz plus some constant. Now if we integrate this equation, this will tell you that P is minus rho gz plus some function of x and y, because it is a partial differential equation. If you take this expression and differentiate partially with respect to z, this function will go to 0. So when you integrate PDEs or partial differential equations, you get arbitrary functions. When you integrate ODEs or ordinary differential equations, you get constants of integration. So that is why ODEs are easier to solve. Okay. Now you want to find this constant c, so use this boundary condition. So if I find this function P of z, which at z equal to h, you see that at z equal to h, P will be minus rho gh plus c. You set this equal to the given condition, atmospheric pressure. So that means that c will be Pa plus rho gh. And hence, if I substitute that back over here, what happens? Okay, so we evaluate this function at z equal to h and set it equal to Pa, that gives you the c. If you plug it back over here, you get the function Pz is Pa plus rho g into h minus z. So this is the solution. Now if I take a point here, this distance is z. Okay, so if I say this height is small h, the depth of this point below the free surface, that is your capital H minus z, because total distance is h. So this is your small h. So what you see here is that if I draw that figure again, this is the surface of the tank. You have air above, water here, you have a point here. This distance is z. this total distance is h. So this much I am calling small h, which is h minus z. So we had Pz is equal to Pa plus rho g into h minus z. So that is Pa plus rho g h. Okay. So you have this standard result that as you move downwards below in the water, the pressure is increasing linearly with this height rho g h. Okay. Now let us consider another example. Let us say we have a inclined plane and you have a tank here. Which is partly full of water. If I say that this is my direction of gravity, okay. Now how will the water level look like in this tank? It will be horizontal because grad P is rho g. Now grad P is a vector which is perpendicular to the surfaces of constant pressure. Okay. Now rho is a scalar, g is vertically downwards, so rho g is a vector which is downwards. So grad P is in this direction. So the surfaces of constant pressure are going to be horizontal surfaces. So this might be P equal to C1 or say A1, this might be P equal to A2 and so on. Now the free surface, at the free surface the pressure is constant, which is the atmospheric pressure. So you are going to have a water level here which is like this. This is your water when it is at rest, and this is air. Now suppose I want to find the net force exerted by the water on the bottom surface of this container. Okay. Now, if you take a point here, it is at a certain depth below the surface. Okay. If I take another point here, it is at a different depth from the surface. So pressure is going to vary, it's not a constant along this bottom surface. So if you want the net force, you have got to integrate. Okay. So you need to know how the pressure at the bottom is varying with some coordinate, and it's convenient if I take x to be this and y to be this, maybe. Okay. If the origin is here, then the net force will be the integral of P at y equal to 0 dA. Okay. So here you cannot take the z axis. If you choose this coordinate system, the z axis is not in this direction. So let us go back and solve that equation again. The basic equation is grad P is equal to rho g. So this I can write as rho into gxi plus gyj plus gzk, where gx, gy, gz are the x, y, z components of the gravity vector, and this will depend on your choice of coordinate system. So the equation that you want to solve is grad P del P del x equal to rho gx. If you equate the I component or the x component, if you equate the y component, you are going to have del P del y is equal to rho gy, and if you look at the del P del z, that is going to be rho gz. Okay. Now we have to integrate partial differential equations. So if I start with the first one, gx, gy, gz are constant, and for the timing we are assuming that rho is a constant, so it's a liquid perhaps. So from here you're going to get P equal to rho g x x plus, let us say, some function of y and z, because the left hand side here involves a partial derivative. This can be a function of y and z. So how to find this y and z? Well, look at del P del y. From here you get del P del y let us differentiate this equation, this relation with respect to y. If you take the partial derivative with respect to y, this goes to 0. You have del of f1 del y. So this must be equal to rho into gy, what you have on the left hand side of this equation. Now, if I integrate this with respect to y, you are going to get f1 is equal to rho gy y plus some f2 of z. Because this was a function of y and z, and I integrated partially with respect to y, this was a function of z only. Okay. So that means from these two, we are getting p, let me write it below here, equal to rho gx x plus rho gy y plus f2 of z. Now we have to find this function f2 of z. To do that, you substitute here, so find del p del z. So when you differentiate partially with respect to z, this term goes to 0, this term goes to 0, you get df2 dz, which is equal to rho gz. So that means that f2 will be rho gz z plus, now you can write it as a constant because this is a total derivative. So if you go back and substitute over here, you get p is equal to rho gx x plus rho gy y plus rho gz z plus c. So this is valid for any coordinate system, whereas the previous result which we got was valid when the z axis was vertical and pointing upwards. Now I will show you another shortcut. If I say p is a function of x, y, z, then you know from your calculus that dp is del p del x dx plus del p del y dy plus del p del z dz. Okay. Now del p del x I can write as rho gx. Del p del y is rho gy, and this is rho gz. Now for the case when rho is a constant, I can write it as d of rho gx x. I can move this rho gx inside. This I can write as d of rho gy into y, and this I can write as d of rho gz into z. Or I can write it as d of rho gx x plus rho gy y plus rho gz z. Okay. Or in other words, I can move these terms on the left hand side, that is d of p minus rho gx x minus rho gy y minus rho gz z is equal to 0. So this will imply that this function is a constant. So p minus rho gx x minus rho gy y minus rho gz z is equal to c. So this is what we had earlier also. Now I can write it in a coordinate invariant manner. If I take the position vector r of a point, that is xi plus yj plus zk, and the g vector we are writing as gxi plus gyj plus gzk. So if you look at g dot r, this scalar product, you are going to get gxx plus gyy plus gzz. So if you go back over here, this whole quantity I can write as rho into g dot r in short. So the hydrostatic pressure distribution we are getting is P is equal to rho g dot r plus c, which is easy for you to recall from memory, or you can write it as rho gx x plus gy y plus gz z plus c. Now let us go back to the special case when I take z to be upwards and g to be downwards. This is x and this is y. So here your gx is 0, gy is 0, and gz is minus g. So if I put these to 0, you will get p is equal to minus rho gz plus c, which is what we had got earlier. But when you write this expression, you have to keep in mind the restriction. That is, you have chosen a coordinate system where z is a vertical coordinate and pointing upwards. If z is vertical and pointing downwards, then this will be plus rho gz. Okay. Whereas this expression you can use for any arbitrary coordinate system with any orientation. Okay, so it is almost time now.